doesn't tell us exactly what they're teaching.
So how can I? Okay, I'm streaming. Let me share.
It doesn't tell us. If you get if you complete the box assignment on CrowdMark by the end of first week of classes, you receive a 1% bonus on exam. Wow, that looks helpful.
Okay, so I'm streaming on YouTube.
Drop the link.
Yeah, send the link. It's unlisted, so you guys can see later.
This fucking thumbnail.
Bro, that's my profile pic, bro. I had it since like grade 10. I have not been bothered to change it.
Oh.
You can tell the sort of things I spend my time on in grade 10. Oh yeah.
Yeah, I can tell. Hello.
Wait, so what are you doing?
Hi.
Hello. What's up?
Oh, hello.
I'm just here to watch y'all through your algebra.
Oh yeah.
There's like 3 people today, bruh.
It
seems like everyone gave up after eigenvalues because well, I think people gave up like way before then.
But the thing is, even
they're
like
not that bad. They're just fucking annoying to compute.
Oh no, like I think people just got lost.
Bro, we're the instructors supposedly, and we haven't even studied this, so it's nobody's prepared. Oh yeah. I'm gonna pretend to be prepared.
The instructors themselves don't even barely know shit.
Wait, where were we?
Okay,
Yeah, so we want to prove
they're
this.
They're only going up to holy shit, they barely do anything. They do determinant, eigenvectors, and eigenvalues.
Bro, get ready to solve 5x5 systems of equations, bro. It's gonna be.
Bro, I hate those. Please give me
Okay. We want to prove this
aren't too hard, though.
For upper triangular, a linear operator with an upper triangular matrix. So how did we do that? I got 10 minutes ago, and I don't remember. Oh yeah. So
we should probably cover the theorem soon. Yeah.
So what do you say?
822 syllabus just dropped, so we'll probably make a session on determinants.
Oh, the exact.
Yeah, I just read though. Schedule? I have access to the course, so.
Oh wait, you're a TA, right?
Yeah, I'm a TA.
Oh yeah.
I'll see you sometime.
Oh yeah. Okay, let's not waste time. We've already wasted too much time.
Like 1 hour of lectures on Friday.
So I gotta go do something. I'll be back.
All right. Have a good one. All right, let's continue.
Okay. So yeah, where were we? Okay, so notice that if the matrix of T is upper triangular, then we know that where TV1 gets sent to, where V1 is the basis. We have the basis V1 to Vn. Keep that in mind. So where does T send V1? It sends it to lambda V1, right? So we already know that with lambda 1 V1. Sorry. So we know that lambda 1 is an eigenvalue. And V1 is the eigenvector. I'm gonna abbreviate them. So what does this mean? So this means that the operator T minus lambda 1I has a root at V1. Well, I don't think I can use the word root, but you get the idea. So what we can do to prove this, we would like to sort of move these around, and we can do that with polynomials. So we define pk to be the polynomial, well, pkz to be the polynomial z minus lambda k. So for example, if we do p1t, it's going to be t minus lambda 1 I. If we do p2t, it's going to be t minus lambda 2I, and so forth. So how does this actually apply to our problem? So we wanted to show that t minus lambda 1I multiplied by all these things to lambda ni is the zero operator. So we can write this in terms of the polynomials we just defined. Those polynomials being these. So we can write this as P1 multiplied all the way to Pn of t is the zero operator. That's what we want to prove. Well, an interesting fact about these polynomials is that, so we said that our matrix is upper triangular. That's sort of important. So if we take pk of t and apply the kth basis vector to it, where does this get sent? Well, this is equal to tvk minus lambda vk, lambda k vk. Notice tvk, if you sort of imagine the kth column of this matrix, it consists of a linear combination of the terms from the first basis vector to the kth basis vector, where the coefficient on the kth basis vector is lambda k. But since we're cutting it off here, we're also, then this whole thing is a linear combination of everything from v1 to vk minus 1, because we cut off the kth one, right? So pk basically takes vk to the span of all the vectors before it. Why does this matter? Because if you want to show that this is the zero operator, we have to show that it sends all the basis vectors to zero. Now we can start with v1, for example. And because we can interchange the order of the multiplication in polynomials, we can rewrite this whole thing as in reverse direction. And we apply v1 to it. This whole thing is equal to Pn to P2 of t times, well, composed with P1 of t, v1, because it's associative, and this whole thing is 0, that is, this is 0, then this whole thing ends up being 0, right? So this operator sends the first basis vector to 0. Now we have to show this for all the other ones, and well, I'll just show you the second one because the rest of them have the same idea how you do it. I'm gonna change color because why not? Okay, so we have Pn all the way to P1 of t applied to V2. We can rewrite this as Pn all the way to P3, then P1, so we skip the second one, and we put it here. But notice what we said here is that pk of t sends vk to something in terms of the previous basis vectors. Right? So p2 of t v2, this thing, is in the span of v1 alone, right? Because we kicked off v2. Because it's the span of v1, then p2 of t v2 is equal to like mu v1 for some mu, where mu is a scalar. So if you rewrite this whole thing, we get Pn all the way to P3, P1 of t mu v1. Well, you can sort of see what happens here, because when we expand this and we get P1 here, it ends up being mu goes out all the way at the end, Pn P3, then P1 of t v1, but we already know that P1 of t v1, we said this here, right? So P1 of t, if you apply this to v1, we get this, that's t v1 minus lambda 1 v1, which, as we know, because this matrix is upper triangular, ends up being 0, right? So this whole thing is 0. So this ends up being 0. Therefore, the whole thing ends up being 0. And so this operator sends the second basis vector to 0. And you can sort of see how you could generalize this with like induction or something to all the other basis vectors. You just move them in a particular order, right? So that the spans get decrease all the way to 0. Oh yeah, where were we? Determination of eigenvalues. Wait. Oh, okay, so when we have an upper triangular matrix, So one of the nice properties that we observed is when you have a linear operator T whose matrix is upper triangular, looking something like this. So we showed that lambda 1, I can actually bring up the thing here. So we showed that lambda 1 is an eigenvalue of T, and V1 is the eigenvector. So can we generalize this? Can we show that the other ones are also eigenvalues? And it turns out that we can. Why can we? Oh yeah. So remember the PKs we defined before? Right? So we defined PK to be Z minus lambda K. Let me see what I think. Okay. Z minus lambda K. And we showed that PK of T is a linear map from the span of all the vectors from V1 to Vk well, wait, we didn't actually show this. So what we showed is it's a linear map that sends Vk to something in the span of the previous vectors. And this is already enough to tell us that Pk of T is not injective. Because it's sending a basis vector to something in terms of the previous vectors.
Ken?
What?
Sorry for the micro. Do you hear me well?
Your voice sort of breaks off a little bit, but yeah, go on.
By any chance?
I'll type it in the chat.
How we define polynomials? Oh yeah. So polynomials, review, basically. So remember how in calc and high school and even before that, maybe, we had these functions, p, and in this book we write them in terms of z because of complex numbers. They were the sum of, power functions, right? So we have a0 plus a1, z1, all the way to an, zn. So these are polynomials. If you have a sum of power functions, you have a polynomial. What do we do when we apply operators to them? What, instead of z, when we put t, right? So t is some operator. That. Okay, so when we were proving this theorem, which in the book is theorem 5.40, or just 5.40, as an auxiliary step, we defined the polynomial pk of z to be z minus lambda k, right? So it's just a equation of a straight line, if you interpret it as a polynomial over R, with the y-intercept being negative lambda k. Yeah, I hope that answers your question. Wait, where were we? Oh no, one of these. Oh yeah. Okay, so we showed that pk of t is not an injective operator. But what is pk of t? So we said that, I was actually about to say that in the lesson. Okay, so pk of t is t minus lambda k multiplied by the identity operator. And this, we showed, is not injective. So if you remember the previous lesson, we know that if a operator like this isn't injective, that means that lambda k is an eigenvalue of T. So we have shown now that the diagonals of an upper triangular matrix are eigenvalues of its operator. Now that's not all the proof. The second half of the proof, which I'm not going to go over because I don't understand it, to be honest.
I just have said it's boring.
Yeah, it's just boring. It's boring. We don't care about it. It shows that these are the only eigenvalues. Yeah, you can look over that yourself. Okay, do we have anything more? Oh yeah, okay, necessary and sufficient conditions to have an upper triangle. Okay, this, I'm just gonna summarize the result. I'm not gonna prove it, the proof is long. That is, T has an upper triangular matrix with respect to some basis of V
Linear algebra done right in Chinese. Well, damn.
if and only if the minimal polynomial of T is of the form for some scalars lambda 1 to lambda m. The proof is long and I didn't read through it because it was long. So yeah. And then the last theorem of this section says that it says that if V is a vector space over the complex numbers, then any operator on it is upper triangular. That is, you can write a matrix of T such that that matrix is upper triangular with respect to some basis. And this follows from this theorem whose proof we skipped. Why does it do that? Because, well, if you have the polynomial, if you have the minimal polynomial of T, P, right, then P can be factored in the complex numbers because the complex numbers are algebraically closed with, m roots. For lambda k in the complex numbers. And since this is the minimal polynomial of this, then this theorem here, implies that T is upper triangular. Upper triangulite. You can have a matrix of T that's upper triangular. Okay, I'm gonna use this paper now because it doesn't have anything on it. Okay, yeah, yeah, I haven't done any problems, so I'm not gonna make you guys do them. Do them later. I'm just gonna.
Bro, I even dropped the problem set for last session.
Bro, I spent like so much time doing problems for chapter 3, and then afterwards, like I'm not even doing access problems. I have to do them later. Oh yeah. Did we go to practicals? Oh, for B50, yeah. Well, you don't. Okay. They usually give you a break in the middle, so go for the first half, then dip in the middle, so you can get the attendance. Also, I'm gonna get water. Hold on. You don't go to practicals? I mean, like if you have a friend who goes, you can get them to send you the link. And
You
then
could skip it for DO instead and go to DO1 instead.
for co-op.
Oh, so I'll just have to miss an hour of DO1 like every week or something.
Wait, there were lectures for co-op? It was just modules. I don't think anybody actually read through the modules. Alright, okay. Okay, let me look through this so I remember what to say, then we'll continue. So you just have like a 5-minute break.
The DoorDash here? Oh yeah, it's almost here.
Alright, this section is not too long. It's just the Greshko and this disk stuff is gonna take a while. Oh yeah. Let's continue. Okay, so we're in the second part of this session, and the main thing we're gonna talk about now are gonna be, so instead of upper triangular matrices, we're gonna talk about diagonal matrices. So what are diagonal matrices? Just like in upper triangular matrices where the diagonal was sort of important, the diagonal is very important now, even more so. But the difference is, whereas before you would have stuff on top as well, now everything on top is 0, everything below is 0, only the diagonal actually has stuff on it. And a lot of the stuff we did analogs, the stuff we did for, upper triangular matrices has analogs in diagonal matrices as well. Well, the first thing I have to define is eigenspaces. So before we actually get to diagonal matrices, we have to talk about eigenspaces. So if you have a linear transformation T, well, I should mention operator. I always just say transformation. Alright, so if you have an operator T, and it has an eigenvalue, so TV is equal to lambda v, then the set of all eigenvectors of lambda actually ends up being a space. Why? Because, well, that's just the null space of t minus lambda I. Notice, if this is 0, right, so if tv minus lambda v is 0, then tv is equal to lambda v, so v is an eigenvector of lambda. So we call this space the eigenspace, and we denote it as E lambda t. That's the eigenspace of lambda. Yeah. Now, eigenspaces are, I guess, important. The first result about eigenspaces, can you guys, if you guys don't see the paper, tell me, because it's
I can see the paper.
yeah. Okay, so
I walked out and talked to this thing, but
bro.
cool.
Oh wait, message. DoorDasher. Okay.
Yeah, I had to walk out. Didn't come. Ow.
Okay, so consider the sum of eigenspaces. Okay, so wait. So we have this linear operator T that has distinct eigenvalues lambda 1 all the way to lambda m. And yeah, so what if we get all the eigenspaces and add them? Why do we do this? I don't know. It just seems fun. Oh wait, actually, wait. Oh, I do know why we do this. Oh yeah, so lambda 1 to lambda m. Suppose we take suppose we take like the eigenvectors, right? So we have v1 to vm. From a result from the previous session, we know that this has to be linearly independent. And because it is linearly independent, the only way to get 0 out of this as a linear combination is only when all the coefficients are 0. That is only when you just add them all as 0. So for example, if you look at this sum now, what it ends up looking like is v1 plus m, where tv1 is equal to lambda 1 v1, and all the way to tvm is equal to lambda m vm. And because of this, we know that this can only be 0 when all of them are 0. Therefore, this sum is direct, if you remember the definition of direct sums. And yeah, and because this, in this sum of subspaces, we don't get anything outside of the original vector space V, right? So this is a subspace of V, and because it is a subspace of V, if we call this like U, then its dimension is necessarily less than the dimension of V. And that's the first theorem on them. Then we actually get to diagonalization. So the conditions for diagonalization, a lot of it is similar-ish, you could say, to upper triangulation. Is that a word? No. So notice that if T is diagonalizable, and we'll call lambda 1 to lambda m the distinct eigenvalues of T. And assume that T is diagonalizable, right? So there exists the basis, V1 to Vn, such that the matrix of T with respect to this basis is upper diagonalizable. So the diagonal of this I'm gonna call mu1, mu n, and then these are all 0. So notice that mu1 to mu n are eigenvalues of T, right? Because what this tells us is that tvk is being sent to mu k vk, right? So all these mu k's, the diagonal, they're all eigenvalues. And furthermore, all of the basis vectors are also eigenvectors, right? So we've shown that. So if you look at 5.55, now we've shown that part A of that implies part B. And then if you have a basis of eigenvectors, right, and you look at the eigenspaces, right, so if you have lambda 1 t all the way to lambda mt, because these are all the eigenvalues, right, the eigenvectors have to belong to some of these, right? So when you add all these up, which is a direct sum as we proved, this must contain all of the basis vectors. And because it contains all the basis vectors, then it's equal to V, right? And as a result, because if you take if this is like U, right, and that's V, because they're equal, they necessarily have the same dimension. And this is for only the case where T is diagonalizable. Yeah, and then this, if you assume that this sum is equal to V, you can also construct very easily a diagonal matrix for T. Because you just take the basis of these and you concatenate them and you get a basis for V with respect to which the matrix is diagonalizable. Fleshing out that proof structure is left to the reader. I don't think that's how Axler does it. But yeah. And then the next theorem, what does it say? Okay, so you have an operator. I'm going to use the same T in LV, and it has n eigenvalues. In an n-dimensional space V, so n is equal to dim V, right? What does this mean? So it means we have the eigenvalues lambda 1 all the way to lambda n, and these are all the eigenvalues. So each of these has a corresponding eigenvector, at least one. So we have this resulting list, and from the theorem that I've mentioned a couple of times now, from the previous session, this list is linearly independent. And because it is just as long as the basis, because it's the same length as the dimension, then it must span the space because it's the right length. Therefore, it is a basis. And because we have a basis of eigenvectors from the theorem that we just proved here, this whole thing up top, which is 5.55 in the book, that means that T is diagonalizable. Yeah. Oh, yeah. Let us continue. I'm just going to skip all the examples because I haven't read them myself. And then this theorem, I'm going to skip again because the proof is very long and very boring. But it's the same thing from before, basically. This one carries straight up from upper triangular matrices that, if V is finite dimensional, then T is diagonalizable if and only if the minimal polynomial P of T, of course, is equal to
I think it froze.
what?
I think the stream froze.
Oh, it froze?
Yeah, it looks like it. Oh, there you go. It's back.
Oh, okay.
Yeah, it freezes sometimes.
Okay. Then then Z minus lambda M.
Is it just you and me left?
Is what?
I think it's just the two of us now, right?
So Catherine might be watching on the stream.
Oh, yeah.
I'm not sure. Bro, that'd be a troll. Okay, Catherine, if you're watching, send the comment. I don't want to stream, just...
For not watching, we can do some group theory instead for fun.
I don't think anybody's watching. Can I see my viewers? Okay, one person watching now. Is that myself?
Because there's one, it's yourself, yeah.
Where's OBS?
You have to open YouTube.
No, I can see it. Okay, it says I have one concurrent viewer.
So that means it's yourself, yeah.
Even on OBS?
Mm-hmm.
Bruh, okay. I guess that was it then. We didn't even get to... Oh.
I think everyone gave up, yeah.
Oh, yeah.
Nope, never mind.
Oh, somebody joined? Oh, yeah. Okay, we shall continue.
I guess we'll continue.
Oh, the quality's bad on Discord? I don't care. I don't know. My streaming setup is very janky. I apologize. Wait. I can do 4K. How for video don't tend to support them?
I don't think you can stream 4K on YouTube because
I
I
can't.
think they restrict your rate. I'm not sure.
Oh yeah, then I'll just keep to 1080p.
1080p was fine.
Where was I? Oh, where are we? Oh yeah, this theorem. Oh yeah, I'm not gonna prove this because I haven't even read the proof. It looks very long. And boring. So yeah. Yeah. So T is diagonalizable if and only if the minimal polynomial looks like that for some list of numbers lambda 1 to lambda m. And 5.65 I'm gonna skip because I don't think anyone actually uses this to do it. Control F 5.65. Okay, it's used one more time in the whole book, so I'm not gonna even go over it.
Just use one more time. Why?
What?
It seems useless if it's used like one time, right?
Yeah, so I'm just gonna skip it. Like, you know.
Good idea.
Nobody cares. Oh yeah, Greshkorin discs. Okay, this one is I actually didn't go over this in full detail. Okay, so what is a Greshkorin disc?
What the fuck is that?
Yeah, that was my reaction when I first saw this.
I've never heard of that.
Okay, so Greshkorin discs. Let's
Let's get that. Sounds fun.
okay, so I'm gonna write the formula down first, so we can just take in the glory. And I'm gonna make up a notation. So, no, she said she's watching the stream, so.
Okay, so I'm gonna Gershwin disc theorem.
Yeah. Okay, so I'm gonna make up my own notation. So we say that the jth Greshkorin disk theorem, not theorem, the jth Greshkorin disk of the matrix A is this set, and then I will probably give some examples. Z in F, and F is assumed to be. Bro, what is a metric field? Do we have a metric field?
Metric field?
Like a field with a metric defined on.
Oh, that's just a metric field. Oh, that's just a ordered field.
Okay, so we have an ordered field.
I know.
Yeah. And
this is why that's not very useful because I think it's only useful to see
no, this is for C as well. But honestly, I think the only reason Axler even does this is because one of the exercises is like find the formula for Fibonacci, the closed form formula, and it uses this. So I just wanted like to do that. That's, I don't know. And this,
I mean, this P items, but I don't think that's complete. It's not a field either. Did you get modules?
Bro, no modules. No more. Modules are hard on, bro. Okay. Yeah, okay, so we have the jth Greshkorin disk of the matrix A is this set. What does this mean? Okay, so I'm going to give an interpretation for R. So if the field we're using is the real numbers, what this ends up being is, and I'm going to write the matrix A down, right? So A I'm gonna assume it's a square matrix. Yeah, so if F is R, if the field we're using is the real numbers, then what this set ends up being, in a sort of geometric sense, is part on the number line, a closed interval, because that's a closed inequality, centered around AJJ, and AJJ, notice, is the jth element of the diagonal, So we say that's AJJ. And it's the closed interval around this point of radius S, right? And this S is equal to this. What is that?
Closed unit size code. Closed disk code.
Closed disk. I mean disk, like, I don't know. Oh yeah.
It's a C.
It's like saying a disk is a disk. Like, I want to explain what it is.
Oh, sure.
Of radius S. And what is S? So S is the sum. And if you look at the sum, because J is fixed, right? We're summing up all the elements in the jth row except the one, because notice K cannot equal J, except the one that lies on the diagonal, right? So for example, if, you know, for the, I'm going to call this actually Sj, right, of radius Sj. So let's compute S1 of A, for the matrix A. So you have to sum up all the elements of this row, excluding the one that lies on the diagonal. And in this one, the only one that lies on the diagonal is A11. So we sum up the rest of them, right? So A12, the absolute value, all the way to A1n. Yeah, and that's the one, that's the interpretation for the real field, the real numbers. And for the complex numbers, I hope you guys can see that. If you say that F is equal to C, well, C is a plane. That's the real axis, that's the imaginary axis. Can I fit this in? Can I somehow fit it in? Oh yeah. So this in the complex plane is going to be a circle, or if you take, say, AJJ here, the jth Greshkorin disk of A is going to be a circle around AJJ of radius Sj, where Sj was defined like this. Wait, you can't see that. Like this. Yeah, yeah, the sum of all the stuff in the row except the element that lies on the diagonal. Now, the Greshkorin disk theorem. Okay, I'm gonna need a lot of space. And I'm gonna use a new color because why not? So the Greshkorin disk theorem, what does it say? It says that, wait, what does it actually say? Forgot. Yeah, so if you have a linear operator T with a basis V1 to Vn. Wait, what does this have to do with diagonalizable? Okay, I don't know. So when you have a basis V1 to Vn, then each eigenvalue of T is in some Greshkorin disk of the matrix of T. And for now, we're going to say that A is the matrix of T with respect to this basis. Let's prove it, I guess. Because I went over the proof. It feels like wasted if I don't prove it. So we have an eigenvalue lambda. That means that there exists some W in V such that TW is equal to lambda W. Now because we have that basis, we can write this whole thing as, say, W is equal to like A1, V1 all the way to AN, VN. Then TW, I'm gonna need a lot of space. So TW will end up being equal to A1 TV1 plus AN TVN, which is equal to lambda A1 V1 plus lambda AN VN. Because W is the eigenvector. Now, because A is the matrix of T, and the columns of A represent where, the basis vectors get sent to, we can expand this whole thing. We can expand this whole thing using A, basically. So what we get is, and I'm going to use, in my own, like when I went over this, I sort of wrote everything as like a table because you can reason about that easier. But I don't have space, so I'm going to use sums. So we can sum this up and we can say, so we have like k from 1 to n of ak times tvk. Now tvk we know is equal to, or at least we can write it as a linear combination using the coefficients of the matrix of A. So the numbers in A, the big A actually, the matrix of T. That ends up being equal to, for like j equals 1 to n, the kth column, right? So 1k v1. Okay. Yeah. This ends up being equal to this. Then we can write everything in terms of, wait, not v1, vj. We can write everything in terms of vj. That ends up being, through some algebra, which I will not do, will be j equals 1 n right? And the way I did this on my own notes, so if you want to do it yourself, like you can make like a table, and then the manipulation is easier to see, what to do. Okay, and this whole thing, of course, is equal to this sum, because we have this thing on top, right? We can write that as a sum as well. As j goes from 1 to n of lambda aj vj. From this, because notice we have the coefficients of all the vj's are these on both sides, so these two must be equal. So we have to say that lambda aj is equal to this sum as k goes from 1 to n of ajk ak. So how does this relate to Greshkorin disks, you say? Well, we have an eigenvalue, and somewhere here we have ajj, right? Somewhere here we have ajj. So that's the only thing we need. So we can move the ajj to this side, right? And that ends up being, now I'm gonna actually write the whole thing down, right? So lambda aj is equal to aj1 a1 all the way to ajn an. From this side, we're gonna move the ajj term, the big ajj term, to this side, so we get, I'm gonna absolute value to keep everything positive. aj1 a1 ajn an. So by the triangle inequality, and this looks, we're getting something looking like Greshkorin disks. Just notice we have, the thing we have here is an absolute value, we have a lambda, we have an ajj. That sort of looks like Greshkorin disks. And if you expand this using, what was the thing? The triangle inequality, we get something sort of looking like this. Because and the other thing you have to remember is, on this side, we don't have ajj. I didn't write it down because it would take too much space, but we don't have ajj here. And that corresponds to this k not equal to j thing on the bottom here. Alright, so we just sort of plow through with the algebra. Triangle inequality, what does it say? We have a1 aj1 plus all the way to an ajn And again, we don't have AJJ here. AJJ is moved to this side. I'm just not writing it to save space. You can factor out AJ here as well. So we say AJ lambda minus AJ J. Looking a lot like Greshkorin disks. If we move this to the other side, we're getting very close to what the definition of a Greshkorin disk would be. We have A1 over AJ, AJ1 plus AN over AJ, AJN. Okay, now we're sort of stuck because if you look at the definition of a Greshkorin disk, there's no coefficient here, right? But we have coefficients here. How do we get rid of these? Well, we just sort of assume something. We say that AJ has to be the maximum of A1 to AJ, which if you recall are the coefficients or W of the coefficients of W with respect to the basis that we chose. But not AJ, AN. So if we choose AJ to be this, then AK over AJ, and because this is the maximum, oh, I have to choose these as absolute values, sorry. And because AJ is bigger than all of these are all less than 1. Less than or equal to 1. Because they're less than or equal to 1, they're making all these big A terms, the matrix terms, they're making them smaller. So if you get rid of those, we get something even bigger. So you can rewrite this as lambda minus AJJ less than or equal to AJ1 plus all the way to AJN. Of course, excluding J itself. Yeah, and this shows that lambda is in the jth Greshkorin disk. Where oh my god. Yeah, and that's the Greshkorin disk theorem. And that's it, I think. Yeah, that's it for diagonalization. We're gonna do commuting operators in like, I don't know, 5 minutes, 10 minutes.
Oh, that's interesting. Reach, yeah, fine. Time fail.
Okay. I'll be honest, I haven't actually read commuting operators, so I have no idea what I'm getting into. Just gonna YOLO this with.
We could also do the thing where we call this, you know?
Call it a day.
We could call it a day.
I mean, like, okay, so the thing is, then chapter 6 is like.
Yeah, I feel like inner products are gonna be more interesting, though.
Bro, honestly, I feel like just Axler just did not care about, like, this chapter it was really boring. Like, I prefer chapter 3 to eigenvalues.
That's true. Yeah, this is what the slow chapters, you know?
Yeah, and he just, like, fact dumps. He just, like.
Yeah, you might not.
Here's a bunch of theorems, you know? Like, who cares?
Boring after a while. Like, this chapter is kind of boring.
Then, what do you need to know for chapter 6 of what we covered generally?
We probably won't.
I'm not sure if we even need these in chapter 6.
I don't know. I think inner products might be asked. I'm not sure.
Oh wait, on A22?
Yeah.
I don't think so. We're gonna do dot product, but we're not gonna
Inner
go into
products
the
are good,
theory,
though.
like
I
orthogonalization
wonder-
and stuff.
I roughly know what it is, but like that's it.
Oh man, the proofs are so long for this section. Bruh.
How
Oh, yeah.
about we just skip the proofs?
If you skip the proofs, you might as well skip the whole thing because I don't know the theorems either. So
Annoying.
Okay then.
so are we just skipping?
This chapter is so goddamn boring. I am going to fucking skip it.
Okay,
To
yeah.
determine-
Fuck it, we're gonna skip. Yeah, maybe
Into-
when we do determinants or something. Actually, fuck it, bro. Okay, if we end up needing commuting operators later on, we'll make like a short session for them or like post notes or something. Yeah. Okay. Okay. Thanks everyone for I guess watching. Yeah.
Eating.
Thank you for teaching.
So yeah.
Having a lot of food.
Do what?
Oh. Wait, first, fuck. 12 p.m.
Bro, your voice cuts out. I don't know.
Sorry, it's 8:48. 12 p.m. Bro, my schedule is so fucked. Like, let's see. So 3 days in a week, I have 3 out of 5 days I have